Hey guys, it's Mia. Today I'll be introducing you guys to signal processing theory. A signal is a description of how one parameter depends on another parameter. Signal processing is an electrical engineering subfield that focuses on analyzing, modifying, or synthesizing signals. Signal processing techniques can improve transmission, storage efficiency, and quality of a signal, as well as emphasize or detect components of interest in a signal. Let's go back in time. In 1948, Claude Shannon wrote a mathematical theory of communication, which laid the groundwork for the development of information communication systems. Digital signal processing started in the 60s and 70s when digital computer became available, but it was only used by the government. In the 80s and 90s, the personal computer revolution commercialized digital signal processing. The predecessor to digital signal processing is analog signal processing, which I will talk about in a second. Although communication systems weren't in place until the 20th century, a lot of mathematical theorems in signal processing come from French mathematicians in the 18th or 19th century. So what are analog and digital signals? Analog signals only exist in nature and they're often sinusoids. We usually see them in electrical circuits. Analog signal processing typically deals with voltage, current, or charge. Digital signals, on the other hand, exist in computers and are discrete, meaning they look boxy. They are much faster to process and more convenient. Digital signal processing is often used to enhance images, recognize and generate speech, compress data, etc. We often want to convert analog signals to digital because, as I've already said, digital is superior. To do that, there are two steps, sampling and quantization. First, we use the sample and hold technique, which only allows output to change at periodic intervals. Then, the analog-digital converter converts the output to the nearest integer number. This is quantization. Unfortunately, this process is often imprecise due to the different nature of the signals. Another way to characterize signals is if they are continuous or discrete time. Continuous time signals have a denominator, or x-axis, that is a continuum. Discrete time signals are defined only at discrete points in time. For signal processing operations, we use calculus for continuous time signals and computers, or computer programming, for discrete time signals. Terms like derivative and integral only apply to continuous signals. For discrete signals, mathematicians use first difference for derivative and running sum for integral, because they're quirky, I guess. Signals can be analog in continuous time and analog in discrete time, or digital in continuous time and digital in discrete time. A signal's y-axis indicates if it's analog or digital, while the signal's x-axis indicates if it's continuous time or discrete time. Signal processing in these categories are often slightly different, but I will be lumping them together for the most part. In signal processing, there are many domains, which is the x-axis. Many of the operations that we will discuss have to do with converting between domains. First, the time domain, in which the graph shows the amplitude of signal with respect to time. There's also the frequency domain, which either shows a phase shift or the magnitude of the signal with respect to frequency. And then the spatial domain, which shows the amplitude with respect to distance. We also have the S domain and the Z domain, which we will talk about later. By the way, the numbers on a domain are called sample numbers. Here are some common signals we may see. First, sinusoids. We love sinusoids for many reasons. All real-world signals can be represented as an infinite sum of sinusoidal functions. Also, sinusoidal functions can be represented in terms of an exponential by the application of Euler's formula. There's also an idea called sinusoidal fidelity, which says that if the input to a signal is a sinusoid, the output is also a sinusoid with the exact same frequency. Another common signal is the impulse, which is just a spike with a super narrow width that starts from 0 that returns to 0. There's a special type of impulse, which is the delta function, also called the unit impulse. The delta function is composed of an amplitude of 0 everywhere except at the sample number 0, in which it has a value of 1. All impulses are just the delta function shifted and scaled. Also, an impulse response is the signal that exits the system when the delta function is the input. Now we have a step signal, which is just a step. It could be up or down. Just like the unit impulse, there's a unit step function, which is a signal that has a magnitude of 0 before the sample number 0, and a magnitude of 1 after the sample number 0. If the input to a system is a unit step, the output is the step response. The step response shows how a system responds to a sudden input, similar to turning on a switch. Fun fact, the period before the output stabilizes is called the transient part of the signal. So we've been talking about outputs and inputs to a system, but what is a system? A system is something that outputs something when it is given an input. There are two types, nonlinear systems and linear systems. Linear systems are just systems that follow the principle of superposition. Superposition is a divide and conquer strategy where the signal is broken down into simple components, each component processed individually, and the results are reunited. Superposition is foundational to digital signal processing. Examples of linear systems include waves, electrical circuits, and a null system. Nonlinear systems, on the other hand, are systems that don't follow the principle of superposition. Examples of these include the power and voltage in a resistor, electronic distortion, etc. Let's go deeper into the principle of superposition. It has two parts, law of additivity and law of homogeneity. The law of additivity means that the sum of the inputs to a system result in an output being the sum of the corresponding outputs. I'm sorry if that was confusing. Essentially, it makes sure that the signals don't interact inside the system. The law of homogeneity means a change in the input signal's amplitude results in the same change in the output signal's amplitude. If the signal follows both of these laws, it follows the principle of superposition and it is linear. A property of linear systems that is not required to be a linear system, but required for digital signal processing is shift invariance. That means a shift in input signals results in nothing more than an identical shift in the output signal. It is important because it means characteristics of systems do not change with time, or whatever the domain is. Once a system becomes nonlinear or non-shift invariant, it becomes a nonlinear differential equations problem, and we do not like that. In fact, the only way to solve a nonlinear system is to make it resemble a linear system. The opposite of superposition is decomposition, which is just breaking signals down. Decomposition should make problems easier. There are many types. The first is impulse decomposition, which breaks signals into impulses. This shows how the system responds to different signals, one sample number at a time. Reminder that samples are the numbers on the x-axis. Next, we have the step decomposition. This breaks signals into steps. This type of decomposition characterizes signals by the difference between adjacent samples. And lastly, we have Fourier decomposition, which breaks a signal into sine and cosine waves. This is insanely important for Fourier analysis, which we will talk about very soon. There are many types of signal processing, including statistical signal processing, which just means using the signal's statistical properties to perform signal processing tasks. Let's talk notation. N is a total number of samples in a signal. The sample index runs from 0 to n-1, like indexes in computer programming. We will start with mean, which is just the mean. It's the sum of all amplitudes divided by the total number of samples, and it's denoted by mu. In electronics, the mean is commonly called the DC or the direct current value. The AC or the alternating current refers to how the signal fluctuates around the mean. Next, we have standard deviation, which is denoted by sigma. It's the square root of the summation of the deviation from the mean squared divided by the total number of samples. The deviation from the mean is squared because averaging is done with power, not amplitude. Because when signals combine, the noise is equal to the combined power of the signals, not the combined amplitude. Sigma squared is actually the equation for variance. Variance is defined as the power of this fluctuation from the mean. This will be important later. Often we want to calculate standard deviation while new data is being added. This is called running statistics. This equation may look messy, but all it is just the mean equation substituted into the standard deviation equation. Something I found interesting in statistical signal processing is that signals formed from random processes usually have a bell-shaped probability density function. This is called the normal distribution, or the Gaussian distribution, or a Gaussian. The total area under it is 1, and you guys have seen it before. Let's move on to some signal processing operations and techniques. One of the most used operations is convolution. It expresses how the shape of one signal is modified by another signal. This star is a symbol for convolution. This equation is a mathematical representation. The weird t is called tau, and it represents the phase shift. Mathematically, convolution is the integral of the product of two functions after one is reversed along the y-axis. The integral is evaluated for all values of shift, and the equation h is reversed and shifted. Here's why convolution is so important. An input signal convolved with the system's impulse response results in the output signal. That means we can find the output of a system given any input in the impulse response of the system. There are a couple common impulse responses used in convolution. May I remind you that an impulse response is a system's output when we input the unit impulse. Convolving any signal with a delta function results in the exact same signal. This means the delta function is an identity for convolution, just like the number 1 is an identity for multiplication. If the delta function is made larger or smaller in amplitude, the system is an amplifier. The delta function with a shift means the system introduces an identical shift between input and output signals. This is called a signal delay or advance. Properties of convolution include it's commutative, associative, distributive, has transference between input and output, meaning a linear change in input results in the same linear change in output. It also follows the central limit theorem, which says a pulse-like signal convolved with itself many times will produce a Gaussian. This is why we see this bell shape so much in nature. A fun fact about convolution is that reverberation is convolution of the original sound with echoes from objects surrounding the sound source. Another operation in signal processing is correlation. Correlation measures similarity between signals. You may notice that it is very similar to convolution. It is almost identical except the second signal is not reversed. The resulting signal is maximized when the two signals are aligned with similar features. Although it is mathematically similar to correlation, it is used very differently. Correlation is used to detect a known waveform in a noisy background, while convolution relates an input signal, output signal, and a system's impulse response. Cross-correlation refers to correlation between two input signals, while autocorrelation refers to correlation between the same signal. This is good for searching for correlation within the signal's own past. The next technique is called Fourier analysis. It's actually a family of operations. There are 4 categories. For signals that are continuous and aperiodic, we use the Fourier transform. For signals that are continuous and periodic, we use the Fourier series. For signals that are discrete and aperiodic, we use the discrete time Fourier transform. And for signals that are discrete and periodic, we use the discrete Fourier transform. All of them are a little bit different, but again, I'm going to be lumping them together. Fourier analysis is the process of decomposing signals into its constituent frequencies, which happen to be sinusoids. We like that because of sinusoidal fidelity, which, if you don't remember, means if the input to a signal is a sinusoid, the output is also a sinusoid with the exact same frequency. Signals that form corners cannot technically become decomposed into sinusoids, but they can get very, 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 very close. In Fourier analysis, one input signal in the time domain results in 2 output signals in the frequency domain. The frequency domain is characterized by amplitude of the sine and cosine waves. There are 2 output signals because there is a real part, which corresponds to the amplitude of cosine waves, and an imaginary part, which corresponds to the amplitude of sine waves. J is an imaginary unit, and omega is frequency. We put these 2 equations together using Euler's formula to form the mathematical equation for the Fourier transform. To change a signal in the frequency domain into the time domain, we use the Fourier transform synthesis equation. Again, using Euler's formula, this becomes the Fourier inversion theorem. We've talked about impulse response and step response. Now it's time for frequency response, which is how a system changes the amplitude and phase of sine or cosine waves of a signal. The Fourier transform of a system's impulse response is its frequency response. Frequency response can be plotted on a linear vertical axis or a logarithmic scale in decibels. In the frequency domain, input spectrum is multiplied by frequency response to get output spectrum. Sounds familiar? It should. This is just like convolution with the impulse response. Linear operations performed in one domain have corresponding operations in the other domain, which are sometimes easier to perform. Convolution in the time domain is the same as multiplication in the frequency domain. This is also called the convolution theorem. However, this is not 1 times 1 multiplication because signals have both real and complex aspects, meaning we have to FOIL. Applications of Fourier analysis include solving differential equations because it may be easier to solve in a different domain, or performing spectral analysis, which means using the Fourier analysis to extract a signal's frequency, phase, and amplitude. This is useful because a function of time has perfect time resolution but no frequency information, while the same signal in the frequency domain has perfect frequency resolution but no time information. More specifically, we use Fourier analysis in the power spectral density function. Let's talk notation. P is power, R is the signal with respect to frequency. The weird curly thing is called psi. It represents frequency. The power spectrum is the plot of this equation. It shows the distribution of power into frequency components, meaning it measures the amount of variance contributed to the data by the frequency. Reminder that variance is the power of fluctuation from the mean. The power spectrum describes how much different frequencies contribute to the mean power of the signal. This is crucial for filter design. Another technique used in signal processing is the Laplace transform. This technique is for continuous time systems with impulse responses that consist of exponentials and sinusoids. The Fourier transform is only applicable for sinusoids. The Laplace transform changes a signal from the time domain to the S domain. The S domain is a complex plane where the y-axis is imaginary and the x-axis is real. The inverse Laplace theorem changes a signal from the S domain to the time domain. If j omega is substituted into S, the Laplace transform is the same as the Fourier transform. This means the Fourier transform is a subset of the Laplace transform. Applications of this technique are, it's often used for analyzing electrical circuits, helps to design analog filters, and it helps to solve differential equations by reducing a linear differential equation into an algebraic equation. The Laplace transform can only be used for continuous time signals, but the Z-transform is its discrete time equivalent. The Z-transform converts a signal in the time domain to the Z domain. Yep, they play fast and loose with the domains. The Z-transform uses the polar coordinate system. By the way, Fourier transform can be done in polar too, but I did not want to research that. This is what Z stands for. Because we are in polar, R is radius and omega is angular distance. Here are some applications of the Z transform. Just like the Laplace transform, it can be used to make analog filters and solve difference equations. Yes, it's difference, not differential. Remember, because they're quirky? The Z transform also helps to design recursive digital filters. By now, you are probably wondering what a filter is. A filter is a device that removes unwanted components from a signal. It has 2 main goals. 1, separate signals that have been combined, and 2, restore signals that have been distorted. Digital filters are superior over analog filters because they are, well, digital. Filters are usually made in either the time domain or spatial domain. Each filter has an impulse response, which in a filter is called the filter kernel, step response, and frequency response. All of these responses give complete information of the signal, but just in different ways. If we know one response, we can calculate the others. The step response is found by doing the running sum of the impulse response. And refresher, the frequency response is found by doing the Fourier analysis of the impulse response. There are many different types of filters, but I will just visit two. A low-pass filter includes a group of small adjacent positive points, and it results in the signal smoothing. A low-pass filter is used for noise reduction, signal separation, wave shaping, etc. A high-pass filter uses a superposition of the delta function, or the unit impulse, minus a low-pass filter kernel. This will subtract low-frequency components from the signal. High-pass filters are commonly used in AC coupling and many different audio systems. There are a couple ways to make filters, but again, I will just visit two. 1. A filter can be made by convolving the input signal with the filter kernel. However, convolution is often long and arduous, so sometimes it must be avoided. The second method is recursion. We add up previous inputs and outputs, all multiplied by coefficients. The coefficients are found by using the Z-transform. How, you ask? I don't know, there is an ungodly amount of math involved. And with that, I will leave you to the rest of your co-education. Thank you for listening.